Okay, linear programming. What we're really going to do is just introduce to you linear programming and really going to give it to you on a simplistic kind of aspect. Linear programming is real life situations. However, in real life, there might be 30 equations. There might be 20 equations that go into figuring out how to either maximize a profit or maybe minimize labor cost or minimize waste or maximize profit, maximize, the whole, what we're doing is looking at how to maximize an aspect of a business or minimize an aspect of a business. You want to minimize maybe your overhead. Maybe you want to minimize your labor. Maybe you want to minimize, as I said, your waste. And you want to maximize things as well. Profit is always the big one to maximize. You want to get the most out of your materials. You want to get the most out of the aspect of what you're dealing with. So with that comes these aspects then. You have constraint inequalities. Constraint inequalities. Constraint inequalities. They constrain you. They constrict you. They limit you. Perhaps you're limited by your warehouse space, and your warehouse space therefore limits how much materials you can have on hand at any given time. Therefore, now if you have a limited amount of materials, let's say you want to work around the clock. Well, great. You might want to desire to work around the clock, but if you work around the clock, you'll run out of materials before the person that's supplying you with materials can give you the next shipment, and therefore you're not going to be able to work around the clock. You're constrained by your warehouse capacity. So even though you may want to work around the clock to produce more product, you can't do it because you can't store that product and be able then to keep working. All kinds of different aspects. So again, in real life, 20 variables, maybe 30 variables, maybe more. Realistically, the way we're looking at it, just a few. So the constraint inequalities constrict the possibility of what you're dealing with. And then with those constraint inequalities, you end up with the intersecting of them, right? We're talking about systems, and you can see in blue there, you've got this region, and this is called the feasible region. The feasible region. So constraint inequalities yield a feasible region. And from that feasible region, then you're able to figure out or determine how to maximize or minimize whatever it is you're looking for. So again, in reality, we're going to look at the simplistic side of this. In real life, the person that would get the big bucks would be the mathematician that would go into a company, would analyze all the aspects of the company, would write the constraint inequalities specifically for that company. We're going to talk about an objective function in a minute, would write the objective function for that company, and therefore then be able to determine how that company can be most profitable, can have the least amount of waste, etc., etc. So again, this is a real life situation, but we're going to take it on a very simplistic approach. All right, so linear programming, technique used to maximize or minimize a particular quantity represented by an objective function. Represented by an objective function. Under a given set of, and here again we go, constraint inequalities. Given under a given set of constraint inequalities. So in real life, this might be, this is going to be a word problem. And from the word problem, you're going to have to then make up your constraint inequalities. You're usually given the objective function. Again, if you were a mathematician, you would go ahead and do it. But problems for you to solve, you can get it a couple different ways. You can get it to where they give you the constraint inequalities, they give you the objective function, and they ask you to maximize it or minimize it. That's what we're going to do, and that's pretty simplistic. You could also, as a student, be given a word problem. And from the word problem, you determine the constraint inequalities. They'll probably still give you the objective function. You determine the constraint inequalities. Sometimes you determine the objective function. From that, then, you're able to figure out how to maximize or minimize. So let me give you the overall concept, and then we'll talk a little bit more about it. So here's a real simplistic example. All right, so find the order pairs that will maximize or minimize the objective function of z equals 3x plus 5y under the following constraints. All right, so in this situation, we've got an objective function. It's here in red, and it gave it to us. The other thing is we're looking to maximize and minimize, and I'll get into that in just a little bit. So what we need to do in this one is, first off, we need to graph what we have here. So we need to graph what's involved. Okay. Let's go through and mark off on our graph. Let's just go straight ones. So I'm going to mark by 5s. So this would be 5, right? And this would be 10. And we'll go by 5s again, up and down as well. So that's 5. Okay, the first situation that we're going to deal with is, and I'll use black, 0 is less than x is less than 10. All right, so what is this telling us? Think about what we've done already this year. Think about what's written there, and tell me, what is this constraining us to? What is this constraining us to? Think about it. 0 is less than x is less than 10. What does that leave us? No guts, no glory. Destiny? Okay, which numbers? Can you be a little bit more specific? Okay, all right, you're partially right, but we got to be a little bit more specific. So she said numbers between 0 and 10. Abigail? What are? Which numbers? I know it seems obvious, but there are two different possibilities. Michelle? Yeah, the x coordinates, right? The domain has to be between 0 and 10, right? Because it said x. So if you wanted to, I mean, you could put a dotted line right here, and you could put a dotted line right here, and the values are between those two lines, right? We can only have x values between 0 and 10, and I dotted both lines because 0 is not considered and 10 is not considered. You know what? I'm going to make it a solid line. I'm going to make life easier. Let's make them equal to. That's what happens when you have first additions. You realize, hey, I need those points. All right, so just make that a solid line because I need those points. I'm going to make the next one solid too because I need those points. Okay, anyhow, it doesn't matter. Okay, so that's the first one. Let's go ahead and use some color. Let's go to the second one in blue. Okay, so that's just an inequality. We know how to graph that. So let's go up to 8 on the y-axis and put a point. And then a slope of down 1 and to the right 5. I'm just going to do it again. puts us right there. And again, let's just, for ease sake, let's just go equal to. We don't want to fool with the dotted lines. Okay, so the shading for this would be below, and I'm really going outside of our area right now, but that's okay because that's just what we need to do. Let's do the last one in green. Okay, so a problem like this last night, you would have solved it for y, and that's what we need to do. So hopefully you look at this and say, I'm going to end up eventually, when I isolate my y, I'm going to multiply by a negative quantity, so I'm going to reverse my inequality symbol. And again, let's just go equal to as well. So the 3x is going to be a negative 3x on the other side, agreed? But it's going to be a negative 3 divided by a negative 10. So a negative divided by a negative is a positive. Are you okay with that? And then 10 divided by negative 10 is going to give us a negative 1. Okay, so we're at negative 1 on the y-intercept. And then we're going to do our slope, right? We're going to go up 3 and to the right 10. And that's going to put us right there. Up 3. So you're at negative 1, right? So when you go up 3, you end up at 2. So you're at 10, 2. And so we have a line right there. I'm going to throw in one more inequality. Let's throw in y greater than or equal to 0. So we'll throw in a fourth constraint inequality. I know you don't have purple, but it doesn't matter. But that's just going to now put us in here. All right, we got stuff everywhere, right? But just like last night, now the feasible region, and this is what you're after, it's going to be where you have the intersection of all the constraint inequalities. So that's going to bring us up here. We got to stop at that point. We're coming over this way. We got to stop at that point. Coming down here. Coming across. Whoops, too low, right? Got to stop at the green line right here, right? Because we are above the green. And I didn't throw in that shading. Right, so stop at your green line and then start coming over. Stop at 0 and come over. And that's your feasible region. Okay. So nothing there was that tricky except the first thing where they just gave you a domain. But again, I gave it to you so you would see it. And now, hopefully, now that you see it, that's not so tricky either. They could do the same thing with the y and give you a range for the y. So don't let that scare you. Just limit yourself to that range. Okay. So what we need to do now is, and here's how you maximize or minimize. So the constraint inequalities give you the feasible region. That's what you wanted. What do you do with the feasible region? You read the corner points. So that's what we need to do now. So you need to read the corner points. So you've got one here. And that first one is what? 0, 8. And I'm just going to come to the left here and write those coordinates, 0, 8. I'm just going to go counterclockwise here. I'm going to go to the next one. The next corner point is what? 10, 7? 10, 6, right? 10, 6. We'll come down to the next one, which is 10, 2. Now this one, we're going to have to guesstimate, right? That one right there. And again, if you were doing all this in real life, you'd have a nice computer model, and it'd give you the exact point, and you'd be ready to roll. We're just trying to learn the concept. So I don't know. I'm going to guess that as a 3.7. Sounds good. And the y is definitely 0. And then we have the corner point of 0, 0. Okay, so we've got 5 corner points. What do you do with the points? You put them in the objective function. So each time we got to run the objective function. So I'm going to put 0 in for the x, and I'm going to put 8 in for the y. So I took my objective function, 3x plus 5y, and now I'm going to do the first point's coordinates, 0 and 8. And all we're left is 5 times 8 for a grand total of 40, right? 3 times 0 is 0, 5 times 8 is 40, and that one's 40. And we're just going to work our way through the points. Now we got 3 times 10 plus 5 times 6. So what is that, 30 and 30? So that's 60. Everybody okay with that? So you get a 30 out of the first one, you get a 30 out of the second one, grand total of 60. And you're just working this all the way down to the end. You're just working it all the way to the end. So we got 40 again. Woohoo, a 3 times 3.7. That's awesome. I hear calculators coming out. Well, come on, 21, 9, 11.1, I think. And the last one's easy, right? It's 0. Okay, so a lot of times in these problems, they'll either tell you to maximize or to minimize. I wanted to do both because I knew I'd only get to probably one example today. So I asked to do both. So here's the reality. If they ask you to maximize, then obviously that's going to be the one where the objective function gives you the max value. And usually a max of z equals 60, and sometimes they want the coordinates of the points. Great. Max of z equals 60, and sometimes you'll use at and give the point coordinates 10, 6. If you're not sure, I'd give them. So if I give you a quiz and you're not sure what to do, I'd give the value of the objective function and the coordinates. Whenever you have a 0, 0 point, that's usually going to be the min, but not every feasible region will have a 0, 0 point. It may not. And a lot of them won't. If I would have had another constraint inequality, don't do this, but let's suppose another constraint inequality came through like that and it was a greater than. Now our whole feasible region we'd have a point here and a point here, and we'd be from there up. So 0, 0 isn't always a corner point or a point of the feasible region, but when it is, it's going to wipe out the variables there, and so obviously the minimum is 0, 0. So min at z equals 0 at 0, 0. So let me go back and try to recap and try to make now sense out of it now that we did it. Okay, what is actually going on here? In real life, this is to maximize aspects of a business or minimize aspects. Maximize profit, maximize materials, minimize labor, minimize overhead, etc., etc. What do you have to do? You have to come up with constraint inequalities. How does the constraint inequalities work? Well, you're constrained by how many materials you have. How many workers do you have? How much work can those workers do in a workday? If you work them overtime, now you're paying them overtime. That's going to change the dynamic. Therefore, now you're paying them more. Therefore, now you're not making as much money off of each of your products because you're paying your workers overtime. So is it worth it to produce more, even though maybe you could sell more if you had that product? But selling more versus the cost of overtime, is it worth it? Maybe not. You got to keep the lights on longer. Okay, you're going to burn more electricity as well, et cetera, et cetera, et cetera, et cetera, all through those different scenarios. So all of that gives you constraint inequalities. When you graph the constraint inequalities, the intersection of them all is going to give you a feasible region. And believe it or not, it's the corner points of the feasible region that matter to maximize or minimize. Because here's the reality, and this is the overall concept. You guys can get this. And I don't have good color here. Here, let me just do it maybe with the magic pen. Okay, that point is definitely a point of the feasible region, right? Put its coordinates in the objective function, you will not get the maximum value. No way. You'll get a value, but it won't be bigger than our 60. You can try it, knock yourself out. Matter of fact, you can try any point you want. Try that point, and you won't get a maximum value. It won't happen. No other point it's going to give you a higher value than our maximum point on the corner. It's the point of what we're doing. Same thing with the minimum. No other point is going to give you a minimum value than that corner point there. That's the aspect of what's going on. So again, what you do is you got to find the corner points of your feasible region, put the coordinates into the objective function. We'll tell you whether to maximize or minimize. And therefore, then you maximize or minimize and figure out then where is the max or where is the min. So tonight, I can't remember whether you guys are 7 through 10, I think they're graphed already. 13 and 16, I can't remember whether you have to graph them and then read your corner points or not. But page 131, 7 through 10. Any questions? Yes, that forever. Nate.
And for the corner points, maybe flexible to maybe like 3 more problems, maybe like
Yes,